All right. Hello, everybody. Welcome back to another exciting edition of the Diffuse Gas and Cosmic Ecosystem Science Interest Group series. So I'm Carlos Vargas from the University of Arizona. I'll be hosting today's meeting. Before we get started, I want to briefly remind everyone of our next meeting after this one. So that's going to be taking place on July 24th, and it'll feature a talk by Carrie Hoadley from the University of Florida. But today, it's my pleasure to introduce Deborah Lokhorst. So Deborah is a research officer at the National Research Council, Canada Herzberg Astronomy and Astrophysics Research Center. She combines instrumentation, observation, theory in really interesting ways to study galaxy formation and evolution, especially in the circumgalactic medium of local galaxies. So Deborah earned her PhD at the University of Toronto Dunlap Institute in 2021 and is the project director and co-PI of Mothra, which is the latest evolution of the Dragonfly telephoto array, which images and maps the circumgalactic medium of local galaxies in three very exciting optical emission lines. So Deborah, please take it away whenever you're ready.
Okay, amazing. Thank you so much for the introduction. That's great. And yes, as mentioned, I will be talking about uh, our latest version of the Dragonfly telephoto array, which we are currently constructing. So I'll be talking about what we're calling now our Pathfinder versions of Mothra. And so I'll be able to show you some results and some imaging that we've already done. But before I get too far into that, I just wanted to give a quick shout out to my co-investigators here. So Bob Abraham at the University of Toronto and Peter Van Dockum at Yale are co-PIs of the project. And then Siri Chen is a grad student who's graduating from the University of Toronto this year, actually, with her PhD. And Will Bowman's a postdoc at Yale, and Ahmad Pasha was a grad student at Yale who's now graduated as well. I just want to give them a shout out because they've done a lot of work towards the project, and of course the rest of our Dragonfly team. Okay, we'll get us started. I, since we're all diffused ionized gas people, this says just a brief refresher for anyone who is likes a little bit of background. I know I do. So these are 10 megaparsec cubes from the Eagle simulation. On the left is the dark matter, which forms this cosmic web pervading the universe, which is this filamentary structure of the intergalactic medium, which um, connects together, and at the nodes are where galaxies form. So in the middle panel is showing the stars, and those are in galaxies, of course. But then on the right, the gas is extremely less coupled to these nodes, and instead flows along the webs of the cosmic web. And it is very important because it is the vast majority of baryonic material in the universe. And one extremely uh, interesting part of the cosmic web is the circumgalactic medium, which is the interface between the intergalactic medium and the galaxies themselves. So by studying the circumgalactic medium, or CGM, we learn how galaxies form, how they evolve, and how they continue fueling star formation. So this is all very interesting. And traditional observational methods of studying the CGM and the intergalactic medium, the IGM, are to use absorption line spectroscopy, which is a very effective way of studying this diffuse gas because it's very sensitive to the diffuse gas. In recent years, like past decade or so, uh, new instruments such as KCWI on Keck and Muse on VLT, these integral field spectrometers have come online and now allow us to do emission mapping of the circumgalactic medium to map out these gas flows, which is very cool. I'm not going to talk about those studies, which have been done by others and they're very interesting. I'm instead going to talk about why we want to use Dragonfly to do this type of investigation. And I'll start by looking at another simulation. So this is little cutout of surface brightness and H alpha emission from the Eagle simulation. And this is looking at like a Milky Way sized galaxy. And the red line around it, I guess I can use my cursor here, is 5 times the half-light radius of the galaxy in the center of this diffuse emission in the circumgalactic medium. And as you can see on the scale bar on the right, this emission spans many orders of magnitude in surface brightness. And if we cut it off, so considering the typical limit for narrowband studies, what observations show is mainly the gas inside of the typical extent of the galaxy, about 5 times that stellar radius. As you push down in surface brightness, more and more of the emission is recovered in observations, but it requires pushing down quite a few orders of magnitude in order to actually image directly this very diffuse emission from outside of the typical extent of the galaxies in this circumgalactic medium. And this is what we're trying to do with Dragonfly in the local universe, is to push down to these surface brightness limits. But this is very difficult to do. Like why the typical limit is this first plot is because there's a lot of sky background and the sky is like thousands of times brighter than this very faint H alpha emission. You can look at other optical lines, which I'll talk about later. O3 in particular and N2 are a couple strong-ish lines in the local universe from the CGM, but they suffer from the same thing, that the sky is very bright and basically washes out this emission from the CGM. So in the local universe, as I mentioned, there's these integral field units with fields of view up to about an arcminute squared. And then there's also narrowband imagers. So the integral field units are doing great work in imaging the CGM emission directly. I've seen amazing results in recent years. And what we're trying to target with Dragonfly is basically closer galaxies where you can see that galaxy itself is studied in detail. And we can also use the large field of view of a narrowband imager to fully map that CGM for these local galaxies that are very well studied, so within the 40 megaparsecs or so. And this is just a view to see why these IFUs are not necessarily the most well suited to studying the really local galaxies. And as you can see, it's because they don't quite, you need a lot of tiling in order to map the whole CGM. Whereas if we could use narrowband imaging, you can take one pointing and recover the whole thing. So this is the idea behind using Dragonfly and whether we can do narrowband imaging with it. So as a background, before I go into what we're currently doing, this is a picture of the Dragonfly telephoto array. So it's a fully refractive telescope, and it has 48 Canon telephoto lenses, which are these off-the-shelf photography lenses that you can just buy. So this is a completely commercial off-the-shelf telescope, and it's a wide field of view imager, about 2 by 3 degrees. And let's see, with 48 lenses, it's equivalent to about a 1 meter diameter telescope. And the reason why you'd want to build such a strange telescope is because these Canon telephoto lenses have these special nanofabricated coatings that reduce reflections. And so you can basically get rid of light scattering in your optics by using a fully refractive telescope and this telescope with these special coatings. By the way, feel free to jump in with any questions at any time. I can't see anybody, so I don't know if you have questions or not, but feel free to shout out if anything's unclear. So this is an example of how the lenses work. So without the special coatings, you end up with these flares, lens flares or ghosting in your images, but they have developed, Canon has developed these nanofabricated coatings, which then they apply to the lenses to get rid of this scattering. And as a comparison, This is the difference between a field from the Sloan survey and Dragonfly. You can see on large scales, Dragonfly does a much better job of removing basically background light that's been scattered around in the optics. Okay, but then how do we actually go after the CDM and IGM with Dragonfly? And as I said, the emission is very faint. So taking the same emission map from Eagle and then creating mock observations, it basically takes like hundreds, if not thousands of hours to actually image this kind of emission. And uh, in order to actually to take an observation of, for example, H alpha or O3 or N2, in you can't just use any old telescope with a narrowband filter. It really needs to be a narrow bandpass filter because, as I mentioned before, the sky is very bright. So in order to remove that background contamination, we need to make basically less than a nanometer wide filters. And this is a figure illustrating why this is very helpful. Um, this is a sky spectrum, and you can see the sky background continuum as well as all of these sky emission lines. And your typical narrowband filter is about the width of this red line, about 10 nanometers. And you can see it contains many of these sky lines inside of its bandpass. In contrast, our filters are less than a nanometer wide, and so they can be put in between these sky lines. This figure also alludes to the fact that we can tune them in wavelength, and I'll get to how we do that in a second. But first I want to motivate why you can't use the filters these narrow in a typical telescope. And that's because typically you have to put your filter behind all your optics where it's inside a converging beam because it's converging onto your detector. And as your filter bandpass gets narrower and narrower, if you put it inside a converging beam, because these filters operate on oh my gosh, interference effect, when you change the angle of incidence, then the bandpass that light sees coming in a different angle of incidence is different from your 0 degrees incidence angle. So, well, you can design to these maroon curves, which are your nice flat typical transmission profiles. What the light actually sees is this blue dash profile when you put it in a converging beam. What we can do with Dragonfly is instead of putting our filters behind the optics where they're in this converging beam, because our telescope is made up of these smaller Canon telephoto lenses where each entrance aperture is about 14 centimeters in diameter, we can actually put these narrowband filters in front of all the optics, and then we can turn that bug of the bandpass depending on the incidence angle into a feature, and actually tilt the filters to scan through different wavelengths. So this is just showing what I just said in a different way. So if you put the filter in front of a telephoto lens at 0 degree angles of incidence, then the light will see this bandpass centered at the design transmission wavelength of the filter. And then if the filter is tilted, say by 10 degrees, that bandpass is actually smoothly shifted by a few nanometers, and the light will see this bandpass at a different wavelength range. So this allows us to use the same filters to look at different wavelengths of light. So we can target both different emission lines with the same filter, and we can target light coming from different velocity structures. And so we basically if they've been blue shifted or red shifted. Here I'm showing, well, the basic effect of having these tiltable filters, which is that what we've created is very much similar to a wide field integral field unit. Um, because what we can also do is micro tilt our filters, and that allows us to step through at an even narrower bandpass than our designed filter bandpass. So this movie is showing a filter, just one of our H-alpha filters, taking an image, and it's being tilted from about 19 degrees to like 14 degrees. And you can see that as it moves in the tilt and we take an image at each tilt, uh, the bandpass is changing across the field of view. Um, yeah, yeah. So one kind of, because our field of view is so large, the the at different sides of our field of view, we actually get an extra tilt, which is why you can see, for example, the skylines passing through our field of view instead of covering the whole field of view at the same time. Um, on the right here is shown a galaxy. So as this is NGC 2403, and once again, as the filter is tilted, it first passes through the H alpha line and then the N2 line. And you can actually see, you can reconstruct from that, for example, a line ratio map or a galactic rotation of NGC 2403, which is shown here on the right. Of course, this requires very careful calibration because basically every single pixel inside our field of view sees a different band pass at one time. And so we are currently working on a very extensive calibration pipeline in order to basically extract a data cube from our imaging so that we can perform a uh, robust analysis of what the H alpha, N2, and O3 look like. Okay, so this brings me to the telescope itself, which is Mothra, and we're still working on the acronym. So we know it has to be called Mothra, but we don't, and then it has to be an acronym, but we haven't exactly picked what it's going to stand for. My vote is multiplexed optical telescope, a hyperspectral refractive array. You can let me know what you think of that, or if you have any other ideas. We're still brainstorming. Nothing's set in stone yet. Set in stone yet. Um, but basically, we're currently embarking on this giant construction project to build Mothra, which will be a 1140 telephoto lens telescope split between 30 mounts. Each telephoto lens gets its own CMOS camera. We're now using 8 cameras. These are also off the shelf. And of our 1140 telephoto lenses, about 950 will be equipped with the ultranarrowband filters. The rest will use background calibration filters. So we have several, 100-ish notch filters of 4 different types. Actually, sorry, I misspoke, of 2 different types. We recently redesigned our notch filters, and also 76 are Sloan RNG filters, and these will be used to get rid of the sky background and galactic contamination. Altogether, the size of this telescope will be equivalent to almost a 5-meter telescope, about 4.8 meters. And the goal, as I mentioned, is to target H alpha, N2, and O3 emission. So we have 3 different types of narrowband filters. Our redshift limit is 0.01, if you can call it that. But we think more in terms of radial velocity. We map all 3 lines out to about 3,000 kilometers per second. And the intrinsic velocity width of our filters is about 400 kilometers per second. But with our micro tilting practice, we can reduce that a lot in terms of our velocity resolution. So down to about 10 kilometers per second. Our pixel scale is about 2 arc seconds. Field of view is large, about 2 degrees by 3 degrees. And we are planning to right now planning to push down below 10 to the minus 20 ergs per second per second squared per arc second squared. Probably we're really aiming for 10 to the minus 21, and we're going to see how that goes. We're putting a lot of new processes in place, which I can talk about. But before I do, I wanted to get into some of our science results so far. Um, if you've heard about this before, you've probably seen results from the three lens array. So this was built a few years back now, and it's based the same idea, but a little bit wider narrow band filter up front, 3 nanometers, because this was to test the concept. And what we did was we did a commissioning observations on the M81 group of galaxies, and we mapped it with the Dragonfly telephoto array, so that original 48 lens array in both G and R to get a nice continuum image, but then also with this 3 lens version of Mothra with this H alpha narrowband filter to look for extended emission in the galaxy. We recovered uh, all features that had been seen before around M82, for example, and then also saw this extended structure in the halo of the galaxy in the intergroup medium. Um, this was a relatively modest exposure for for us, especially because it was only 3 lenses. So this kind of thing can be done and will be able to be done in just a few minutes with the full array once Mothra is finished being built. Um, and even with just the Pathfinder, we reached about a few times 10 to the minus 19 ergs per centimeter squared per second per arc second squared. And then just as an example, the N2 over H alpha maps. So with this Pathfinder, we used the same filter to map both H alpha and N2 independently. With Mothra, we have separate filters for N2 and H alpha. You can still go and use the same filter for them both, but just in terms of for efficiency, we have 2 different filters to map them separately. And then you can do different kinds of science that we're planning to do with our multiple lines that we cover. So we can look for shocks, especially with our updated O3, with our inclusion of the O3 filters, we'll be able to make kind of a BPT diagram analysis for these galaxies. So that's something we're looking forward to doing. And this is new results. So over the past couple of years, I've led the construction of our 110 lens version, which was going to be the final version until we got more funding. Now it's 1,000 lenses. And we spent about 2 years building this. And that does not scale to how fast Mothra is going to be built, by the way. I will tell you more about our construction timeline, which is a year and a half. But I'll get into that in a second. I just want to finish with our commissioning results from the 110 lens array. This one did have O3 filters, as well as a filter to look at H alpha and N2 and a bunch of off-band filters. We basically just spent 1 or 2 months collecting commissioning observations, and this telescope has already been deconstructed, 3 of these, and only one of the mounts is still on sky. The rest have been shipped down to where we're building the Mothra telescope. But anyway, I get ahead of myself. The results for this, for our commissioning, we took data on several galaxies. The Siri Chen, who's a really great PhD student who's graduating, as I mentioned, she's submitted a paper about 3 of the galaxies in this commissioning sample. So 6946 is one of them. And we've got NGC 891 and NGC 7479. So these are the H alpha images from the commissioning observations. We picked galaxies with a range of recessional velocity. So NGC 6946 is the closest to local rest frame for the H alpha emission at 40 kilometers per second. NGC 891 is a bit farther out at about 500, and then NGC 7479 is really our target where we're going to be focusing most of our observations, which is around 2,000 to 3,000 kilometers per second in recessional velocity. And this was our commissioning observations really focused on testing our background subtraction and how our surface brightness depth. Um, as we get close, as the velocity gets closer to zero, there's more and more contamination from the Milky Way, which is why we're focusing on these higher velocity targets for our full survey. Um, so I'll just talk about them each individually, but first I just wanted to mention we didn't get the same exposure depth on every single one of these frames. So 6946 is our deepest exposure with almost 25, more than 2,500 frames on H alpha. 891 had about 700 and 7479 had 1,000. So these are 15-minute images, each of them. But it doesn't actually add up to too much time on telescope because this is just for one lens. And for example, for Mothra, we're going to have 1,000 lenses. For this, only had 100 lenses, so it wasn't actually too, it looks like a lot of frames, so it wasn't too much time. The surface brightness limits that were reached in the commissioning observations go down to like 10 to the minus 20 to maybe a few times 10 to the minus 19, which is what we expected to reach for this data. We were taking shorter exposures than we are planning to take, and there's more electronic like readout noise in our images. So this matches up with our expectations. And the way we're doing our surface brightness calculation, I'm just showing it here to show why we're happy with our surface brightness limits, is we're using this SB contrast method, which basically contrasts a specific size region against the background, avoids extrapolation, and it allows, like if there's a gradient, it only compares your specific size region against the local background. So it gives a more accurate measurement of your surface brightness limit. And basically these are the surface brightness limit as a function of the numbers of your frame in the stack. And you expect that your surface brightness limit should follow these lines, which is the Poisson assumption of noise. And you can see they do follow the lines for most of these curves, which are the different scales on which we calculate the surface brightness. So going from about 10 arc seconds to 240 arc second scales. You can see that for the smaller scales, it holds quite nicely. As you get to these larger scales, it starts departing and the noises increase, is not following the same Poisson. It's not dropping with the Poisson noise threshold. And that's actually to be expected because our reduction process and calibration process was not designed to recover that large of features currently in our current data reduction pipeline. So that's something that we're adjusting and that should be sorted out. But yeah, basically it means that you can't trust features on these. Well, you can trust them, but they're not going to be as deep on these larger scales. Okay, so looking at the images themselves, this is NDC 6946, and these is an example of the different data products that we are collecting. So in the middle column is our different lines, H alpha, N2, and O3. And then the other data is all the off-band calibration frames. There's a whole pipeline to calibrate and subtract the continuum and the galactic emission, like Cirrus, from all the data, and then you end up with, for example, an H alpha image. So as I mentioned before, NGC 6946 is the deepest of our commissioning observations, but it was only about less than 4 hours with the array, with the 110 lens array, which had 60 lenses. You might notice it was less time with O3, and that's because a bunch of our O3 cameras weren't working for a long time, but that problem has been, well, avoided because we're now moving and making a new telescope. So here's the galaxy itself. The previous H alpha image, I'm showing here for comparison, the deepest H alpha image I'm showing for comparison. So you can see once it, like where similar to the Pathfinder results from the three lens array, we're really looking at this larger field of view, larger scale emission. Um, in this field, pretty much all these large features you're seeing are not very exciting to us particularly. They're galactic, most likely galactic in origin, and that is the difficulty with looking at these very low recessional velocity galaxies, of course. But there are some cool things in here. For example, there's kind of this arc of emission near the galaxy that kind of looks like a bow shock. Um, there's, let's see, some new H2 regions that we were able to map because our field of view is a little bit bigger. So you can pick out some stuff from these low redshift targets. Sorry, low redshift, well, very low redshift, basically local targets. But our main goal is to map these higher recessional velocity targets. Yes, so the biggest thing we were wondering if this was connected to the galaxy is this panhandle. Um, but we're quite sure that it's actually part of the Milky Way galaxy. We were hoping it might be connected to NGC 69946, but just a chance projection, unfortunately. Okay, I wanted to also show NGC 891. So similarly, we have this suite of background images as well as the images on the specific lines. This galaxy is a little farther out, so it has less galactic contamination. I think it's also in a less crowded area in terms of the galaxy itself, but I could be wrong. Anyway, I'll move on. But there was one cool source of emission in this field, which was this blob, which seems to be connected to an arc around this other galaxy, UGC 1807. We did follow up with Keck spectroscopy on this blob and found that it's right centered at the velocity of the Milky Way, so it is galactic once again. So that's a bit disappointing, but otherwise a very clean image here. Sorry, and please ignore this, these estimates. This is for the previous galaxy. Okay, and then NGC 7479. This is an interesting case because there's a lot of galactic cirrus in the surroundings of the galaxy. You can especially see in these background images. It's very like wavy looking, but our background subtraction pretty cleanly gets rid of that. Like I'd say very cleanly, not just pretty cleanly. You can see the backgrounds are very flat, so our continuum subtraction process works quite well. This is also a very clean field, so we're not going deep enough yet in this field to detect any extended emission, but we'll be coming back to this with more, or actually I don't know if we will, because we're changing hemispheres, but we'll definitely be doing longer exposures on galaxies, and this is a nice confirmation that we can remove that galactic cirrus, so we don't have to worry about it in our data. And then I just wanted to mention we, of course, can make these line ratio maps. And I'm not going to talk too much about them, but yeah, they basically show your line ratio maps. Right now, we're just inside the galaxy because our data isn't deep enough to look in the halos. But our hope is, of course, to map these line ratios into the CGM and look for the mechanisms, ionization mechanisms, and really figure out these processes that are going on inside the CGM. Yeah, I'm gonna move on. Feel free to ask questions about this if you want. But I'm gonna keep us moving on to our 1140 lens array. So this is the full Mothra telescope. So this is, of course, an artist's rendition of the telescope. It'll actually have, there's 2 mounts missing in this rendition. We're going to have 15 mounts in 2 different enclosures. We're moving the telescope. So the Dragonfly spectral line mapper and the Pathfinder version were all in New Mexico, but we're moving everything down south. We're moving to another privately owned observatory called Alsace Observatorio, which is run by OBSTEC. Um, and it's near La Serena. And so we've yeah, we're building this whole new structures and whole new array down there. Um, as I mentioned, we're currently here. We just started construction. So this is a bird's eye view of the observatory where we are currently building and we'll be hosting Mothra. Um, we have these two different locations, which are, I think, about 100 meters apart. I measured it and now I forget what it is. But the separate locations also help us with removing satellites from our data if it was an issue. I don't think it's an issue in our narrowband imaging, but it has been an issue in our broadband, so our off-band imaging for sure. The first enclosure, which will hold the first 15 mounts, was completed in March. No, it was completed a little bit. It was like completed in like February, March. Our second enclosure was completed in April, May this year. We've just in May, we started constructing the very first mount, and it's now constructed. So this is a video from yesterday. Sorry, it's a bit. Let me see if I can fix it. We literally just finished building the very first mount. This was a testing of the slewing of the mount that we carried out on a Zoom call yesterday. I was here in Canada. This is Emiliana, one of our staff members at the observatory, and he was performing a test of the slewing action of the telescope. So on each array, we have a mix of the O3, N2, and H alpha filters. And we also have 4 off-band filters, which look darker in here because they don't have the shiny filters, which are basically mirrors at the front of the array. So this was very successful. We were actually like really happy to have finished this. And yeah, where our goal is to have this on Sky by June 30th, which is in 4 days. And depending on the weather, we might have the pointing model done by then and have taken our first data with the very first mount of Mothra. So knock on wood, hopefully that goes well. Our construction timeline is 18 months. So all mounts are planned to be finished by December 2026. And then we'll have 1,140 units on Sky for observations after that. As we build them, though, they'll immediately go on Sky. So you can see we're finished one mount. This should be starting calibration as soon as the weather is good and the pointing model is good. It is the winter for Chile now, so as a new Chile observer, I don't know how the weather is in general in the winter, but hopefully we'll be taking data and on Sky to start our survey very soon. So I will end with that. And thank you very much for having me to give a seminar at the talk. It's a pleasure to be able to talk about Dragonfly to all you guys. Thanks.
Wow, thank you so much, Deb. Some incredibly exciting results. I'm going to use my host privilege to actually kick us off with the first question. Uh,
Okay.
so I'm just wondering, so is alignment an issue? So if you're going to need to align, many of these, telephoto lenses, what are the alignment tolerances that you need to reach to do that?
Yeah, luckily they're not very high. So we did do a very thorough calculation of our tolerances when we were designing the cell, like the honeycomb basically structure that the lenses go into, and then the lens mounting block. Basically, lenses get fixed at one end, and then they kind of rest inside a baffle on the other end, which doesn't really hold them in place. And with all the tolerances, we have a offset of about up to like 10 arc minutes max. But that's actually something we want because that allows us to rule out like systematic errors in our array. So we actually usually try to build in an offset. So we in the 110 version, we more carefully control the alignment and then offset it on purpose. And in this one, we're kind of letting the tolerances randomize it, and then we're gonna go in and do adjustments. So we do have like a little screw, push screw kind of um, mechanism, basically, to adjust the alignment in case it's really out. But it's more of a feature for us to try and randomize the pointing. And then sorry to continue, each filter tilter, which is what we call where the filters go into, gets calibrated independently. So it doesn't depend on like the alignment of the other lenses. So each one is an independently calibrated unit.
Awesome. Extremely clever. Thank you.
Yeah.
Let me go to Erica Hamden.
So I this was awesome, and I like could look at these pictures all day. They're like so incredible and very cool. Um, I actually like didn't have a particular question because you answered them as you were going along. Like I'm especially interested in the sky background subtractions.
Yeah.
I'll probably just read your papers, but I don't think that Mothra needs to be an acronym. I hate acronyms, and I feel like you should just call it
Oh,
that. It's fine. It doesn't have to
we
be an
hate them
acronym.
also. Okay, the problem is it's trademarked. So we could get in trouble
But
legally if
okay.
it's not an acronym. But I don't know. Maybe we can just get around. I think we're just gonna get around calling it Mothra. The problem is that we have to have an acronym. Anyway, we're just gonna call it Mothra.
Okay. Well,
Which
that's actually the only
you
good
know
reason.
in your hearts it's just called Mothra.
Okay, I guess that's
For
what
legal
matters.
reasons, there's an acronym.
That's the legal reasons is the only good reason to have an acronym.
Yeah, right, exactly.
Thank you, Deb.
Thanks.
Great. Any other questions?
Hello.
Hello.
Yeah.
Oh, yeah,
Hi,
go.
Deb. Yeah, just have a quick question. So, what about temperature change on the filter? Yeah. If there's any temperature change, are you worry about the transmission
Uh,
for the filter?
yeah, we did test that, and these filters are not sensitive to temperature differences. So we have thoroughly tested it. Um, I can't even remember the exact results because it was like picometers that it would change. Um, I can, if you remind me, I can go look up the plot, but uh yeah, we did look at it and it was basically undiscernible for the filters. That said, one thing we can do is just recalibrate our filters once for different temperatures, and then we can go from there. But that is something that we are like the filter calibration is basically a very we have to be very as precise as possible. So yeah, luckily temperature doesn't seem to matter too much, but definitely yeah, definitely it's gonna be a tricky
Yeah.
thing to do.
Yep. Thanks. Yeah. Yeah. Very exciting. Yeah.
Thanks.
Great. I saw a hand briefly go up and then go down. Was there another question there? Oh,
Was this survey
I
plan?
think I see in the chat. Would there be what would be the survey plan with Mothra?
Yeah, that's a great question. Because in some ways we're still flying by the seat of our pants because we have designed a survey plan for the northern hemisphere. And now we've moved to the southern hemisphere, so our targets need to be updated. But the idea is we're in this strange situation where we're actually funded by a privately, and we need to basically produce and we we really want to meet our first target, which is also which is to just map out the CGM of one galaxy. And we haven't picked which galaxy that is yet. And so if people do have suggestions, let us know because now that we're starting observing, we're going to be focusing on actually picking that target. So yeah. So the idea first is to basically spend months on like one target to map it out. And then we're going to do a series of other surveys, like dwarf galaxies, for example, and then like Edge-ons, star forming sample, that kind of thing. Uh, so it's going to be a lot of data coming in after that first campaign on one galaxy.
I will say if you are looking for targets,
We are.
so Aspera is launching in May of next year, 2026. So the timing is
Yes.
pretty close actually. And I'm lobbying for one of our first targets to be NGC 4631. Since we'll be mapping O6 with Aspera, and that's the only, well, one of only a few galaxies with O6 emission detection. So that might be some interesting synergy there.
Nice. Is that the whale? Am I?
Yes, yeah.
Yes. Okay, yes. I think we actually have looked at that, and that might be on our list already.
Awesome.
Okay,
Uh,
thanks.
Another question to Nicholas.
Yeah, hi. Thanks for the very impressive talk and a very impressive project. Are there other calibration issues that you know is going to be a challenge or that you have control? Like in particular, how do you control those tilts sufficiently that you have the same wavelength for all of the 1,000 lenses?
Yeah, that is you've hit it on the head. That's our main calibration problem. Can I go? Make sure. No.
And then how much data actually what's the data rate of this?
Um, yeah, it's gigantic. I'm not the data person. Sorry. But if I, so basically what happened, yeah, okay, first to your first question, the hardest thing to calibrate out is going to be determining where in our field of view we're actually sensitive to the line, and then modeling and subtracting out the sky background lines in particular. So our first target is going to be picked mainly to avoid skylines. So we're going to look somewhere where we won't be where we won't have that skyline interference. But as you can see, even in this image, if you can pick it out on your computer, there's this skyline coming straight through our image. There's one here. Correctly modeling and subtracting that is going to be our hardest challenge. Right now, we're building a laser calibration unit with a tunable laser, which will allow us to basically create these mock skyline images and then subtract those from our data. Another thing we're going to do is we have a 1 meter telescope down there, and we're putting a spectrometer on it. And our first plan with that spectrometer is to just monitor the skylines at all times during our observations so that we know where they are. And this will help us with modeling them, like with our tunable laser. Then we can tune it to the wavelength of the skyline, take an image, and then subtract it, basically fit, subtract. Yes. And I say all these things as if we know exactly how we're going to do them, but we're currently building those calibration units right now. So we're trying to figure out exactly how they're going to work. So that's going to be a big test in the next year, basically, as we bring our first units online, is how we're going to do those calibration procedures. In terms of knowing our bandpass across the field of view, we will first we do collect all our transmission profiles for all the filters. So we can use those, like that would be the cleanest thing would be to use those transmission profiles and then model their shift across the field of view. And then we know exactly what the transmission is on each pixel. The secondary thing that we're going to do is use all our background stars in basically a intensive modeling calibration to try to map out again the basically the band pass that each of these stars is seeing by like comparing to Sloan or whatever. And then yeah, we haven't designed it yet, but we have two software engineers working on that problem right now. So the first thing is, of course, to know where your bandpass is, but then in case we get it wrong, we're going to use the stars to basically adjust and recalibrate. So that's our plan right now. And so yeah, we'll keep you posted on how it goes.
Thank you.
Oh,
Fantastic.
yeah. And then data rate, it's extremely high because we're going to have 1,000 of these and we're planning to take 15 to 20-minute exposures. I think it actually rivals like LSST in the amount of data that we're going to produce, which is crazy. So we have two people right now, and probably we'll have more just working on our data server side of things and data storage. And we're going to have a big data center basically to store the data and process the data because it's kind of insane. And then we have all these. We actually at the observatory, they put in a whole new downlink for us, like a whole new set of antennas so that we can transfer the data quickly. And lots of new fiber, that kind of thing. And then these like radio downlinks, new antennas. So it's a whole thing. Lots of facility upgrades. Yeah, do I have the number really quickly? Yeah, sorry, I don't have the number. I will try and get that. But yeah.
Yeah, and hey, Deb, another question too that also came up in the chat. I was also wondering, so is there like an analogous cost cap to this? Like how much funding is there for Mothra? And I'm also curious if you're allowed to say what's the funding entity.
Yes. So the funder is actually a private donor. And once originally they wanted to be anonymous. And you're recording this, right? But I think
Recording it, so just want to make that clear.
you are. Yes. But I think they've actually changed their mind. So we're doing a press release. We were actually supposed to do it in June, but it's already the end of June. So hopefully this summer there will be a press release out, and then I think we're going to be naming the donor at that point. But yeah, this is what I can say is the 110 lens version cost 5 million, and this is 10 times that. It's the US. So yeah.
Awesome, good to know. Well,
Yeah.
that's very exciting. I'll be on the lookout for that press release.
Yeah. 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 And then series paper should be out soon. I think it's yeah, almost about to be accepted, hopefully. So we'll feel free to keep an eye out for that as well with the commissioning data from the 110 lens.
Great. Briefly skimming the chat to lots of thanks. And also Xiaowen has my back on NGC 4631. So
Okay. Nice. I've got it written down. So
Great.
if we do it, it's because of you guys, obviously.
Yeah, that has the extended H1 filaments detected from recent fast observation.
Yes,
Then-
I remember. Really beautiful.
Yeah.
I think it's a great target.
Great. Any other questions from anybody before we call it? All right. Well, thanks again, Deb. Incredible talk.
Thank you.
Really appreciate it. And again, our next one of these series will be on July 24th. See y'all then.
Thank
Thank you.
you.
Bye.
Thank you, Deb. That was so great.
Thanks. See you guys.